Okay. So, chemistry is the scientific study of matter. Before the day is out, we're going to start talking about matter. But let's think a bit about measurement. Because if matter is that thing, that tangible thing in the universe that exists, and we know it exists because we can see it, we can touch it, we can experience it. It exists, therefore it can be measured, it has a mass and a volume and all of those other things, then at some point we will want to measure it. So let's think about how do we take measurements? How do we take measurements correctly? And what to watch out for to kind of point us along the way of, oh, no, you're doing that wrong. Because there's a couple of things that you can do wrong. And some of them are more forgivable than others. Okay? Some of them are more inevitable than others and cannot be avoided. But there are some mistakes when you do make a measurement where you can avoid it. And that's where good practice comes in. All right, so let's think about measurement. All right, so the things that we can quantify. We're teaching another class right now, it's called quantitative chemical analysis. And in day one, we talked exactly about what quantitation means. What do you think quantitation means? The word quantity in it. It means putting a number to something. Okay. There's another part of chemistry where you would have done this maybe in high school or even middle school, where you're given a sample and you've got litmus paper, one's red and one's blue, and you stick the paper in the sample, which is not what you're supposed to do. And the blue goes red. Hey, something happened. That tells me that what I was looking at was an acid because the litmus has turned red. That's a qualitative method. That just changed color. We weren't measuring a number. It gave us an indication. So you do how do you know a reaction works? Well, it caught fire. It went purple, it changed color, it emitted gas. These are things that you can qualitatively say happened. But then we've got measurements which are quantitative. Let's think of what types of quantity, just as people, we could measure. Just start throwing some things out. Because I'm going to put them into two types. Measurements. Population. Okay, so that's just a straight count. You're just counting a number, right? So, is that temperature? Okay, let me do that. So, I'm going to put these into two caps. They're called fundamental and derived. Now I know what they're going into before we start. You're going to kind of help you figure it out. So the first one that came out was population. Population is, if I want to count the population of this room, I just count the number of heads going around the class because that's visibly what I can see. So that's just a number count, okay? That's my abbreviation for number. It's an N with a superscripted O. Has a little line underneath the O as well. You may or may not have seen that before. Okay, so that's as fundamental as it gets. That's just a quantity, okay? Someone said temperature. Ooh, that's a good one. We're going to actually spend a moment of time talking about that, probably Friday. Temperature is a fundamental quantity. Fundamental. We'll figure out if we not understand what fundamental means at the end. Speed. Speed. Speed is a derived value. How would you measure speed? Miles per hour is the one that we're most familiar with.
Kilometers per hour.
Kilometers per hour, if you're anywhere in the world other than like a handful of countries. Miles per hour here, kilometers per hour in Canada, kilometers per hour in Mexico, kilometers per hour, I'm fairly confident in the rest of South America and Europe and Australia. Australia still keep hold of the mile. Might be talking out of turn with the Australians, but probably kilometers. Big difference between miles and kilometers. Big difference. We'll come back to that eventually. We're going to come back to that. What else have I got? Could you measure?
Distance.
Just distance from this point to that point, okay? That's really, really simple thing to do. It's in this camp. What else? Oh, there's a cup in the room. There's not supposed to be cups in the room because this room moonlights as a lab. Ooh, altitude. Well, what is altitude? It's a fancy way of saying a distance, isn't it? Okay. So altitude is a specific distance. It's how high vertically are you from the surface of the planet, but it's still a distance. So altitudes, when you're on the plane, what do they measure altitude in? You ever been on a plane? It's kind of cool. And they say, we'll be cruising at, yeah, the American Airlines give you that number in feet. They'll say 20-something thousand feet if it's a domestic flight, 30,000 feet if it's a international flight.
Meters?
Or in meters. And there's a difference between feet and meters. Before the term is over, I'm going to incorrectly call this object right here a yardstick. Not a yardstick. It's a meter stick. It's just like a yardstick, only it's like this much taller. Okay. But there's a huge difference between yards and meters, even though they're physically really, really similar. The difference between a yard and a meter is like this much difference here at the top. And yet, the math that underpins the meter is incredibly easy to use, and the math that underpins the yard is impossible to use. So we will not be using feet or inches or yards or miles. Those are forbidden. We can't use them. In fact, when we finally do get to do a lab by physically being in this room and measuring stuff, which is not going to happen until week 3 because next week we have Labor Day. You've all earned a day off, apparently. So because the Monday lab can't meet, that means no labs will meet that week. But when we do finally come back and measure something in week 3, there's a little note on the first page of the lab procedures that says, this experiment is impossible if you use inches and ounces. It just cannot be performed. You have to use the metric quantities. Okay, what else we got? Ooh, pressure. We measure pressure of gases. Solids don't have a pressure, and liquids have a very, very small, called a vapor pressure. Pressure belongs over here. Pressure is something that we experience when the atoms of a gas that are moving because they have kinetic energy. Remember kinetic energy from high school, middle school, whatever? That's the energy associated with motion. Kinetic energy, this gas particle bounces off an object. If this object is the wall of the container, then that bouncing causes a force. Oh, so now we're talking about, this sounds a little bit complicated because I have a moving particle which has force, Newton, and then it's bouncing, so I've got an impact, and I'm transferring the momentum associated with that force into the wall. And is the wall this big, or is it that big? So it depends on the size of the wall. There's multiple things going on before you can figure out what pressure is. Like goes in this column. And then volume. Where do you think volume goes? Okay, show of hands. And it's okay if you don't know. We're not expecting you to know. We're going to teach you. Okay. Who thinks that volume, it's kind of simple, right? That's a leading. If I'm leading you, I'm never going to lead you to the correct answer. It's a personality trait. I'm going to lead you to the wrong answer and then go, ha, you did, but you didn't think about this. Volume seems like kind of simple, right? Or is there more to it? So hands up, who thinks it's this one? Bearing in mind that me leading you to the wrong answer might have been a double cross, and I might have made you think that this one was too simple to be true and therefore it must be over there, when in fact I'm tricking you that it really is simple and it should be here. Sorry. Who thinks it's here? Yeah, all right. It's not, it's over here. All right, so let's take a second to figure out what volume is. How do we measure, what's our unit of measurement for volume? I guarantee that you all buy liquids.
Milliliters.
You all buy liquids at some time during the week. In what form did you buy those liquids? If you're buying your liquids in milliliters, that's great. But what liquid are you buying where in the US they dispense it in milliliters? I don't know. Okay. Which liquid do you buy that's dispensed in liters?
Water.
Oh, you can buy liters of water. But if you buy bottles of soda from the machine or jugs of milk from the supermarket or gasoline to put in your almost extinct motor vehicle at this point. Yeah, we buy in this country, we buy liquids in gallons and quarts and pints. And that has to stop, because we're going to do an experiment. First physical in-person experiment we're going to do. Next week, there's an online version of the experiment we're going to do, and it will become abundantly clear that the math does not work The math is impossible if you try to do it in gallons and pints and quarts and ounces. Doesn't work. It has to be in liters, and then this other thing called milliliters. Does anybody know what the difference between a milliliter and a liter is? And again, I don't expect you to. It's what we're going to teach you.
It's smaller than a liter.
A milliliter is smaller than a liter. Do we know by how much?
100.
Go ahead.
No, like
100 would be centi.
1,000.
Milli means 1,000. Thousandth. So there are 1,000 milliliters in a liter. Just out of curiosity, how many millimeters do you think are in a meter? 1,000. How many fluid ounces are in a gallon? We don't know. Nobody knows. It's a mystery. Nobody knows. Somebody knows. And the funny thing is, depending on which side of the Atlantic you ask, you get two different answers, both of which are correct. Because in England, the pint, we invented it, is 20 fluid ounces. In the United States, you didn't invent it, it's 16 fluid ounces. And because there are 8 pints in a gallon, an American gallon is not the same value as a British gallon. And curiously, you cannot buy anything in the UK that is a gallon. Gasoline is dispensed in liters. Milk is purchased in liters. We went metric. They had to drag us kicking and screaming, like they're going to drag you kicking and screaming, or your grandkids, I think, kicking and screaming. But yeah, everybody went metric. Still a couple of things missing. Time.
Fundamentals. Fundamental.
Time is time. There's no messing with it, right? It is what it is. It doesn't depend on anything else. Belongs over here. What else? What else could we possibly measure?
Height and weight. Height and weight.
So height is a distance. Okay, that one's already on the board. But weight, I was going to say, oh, where did we put them away? I was going to say, look around the room and see what you can see. We took the balances out. We usually have balances stuck out on the sides of the room. So you can measure something's mass. I'm not going to use the word weight. I'm going to tell you why in a second. We're going to use the word mass. And then you said force, right? Okay. Force. Does that sound... Which side of the board does that sound like? Belongs over here. Because force is associated with motion, and motion just, once you think that this is something that's got to do with motion, then you're talking about a distance traveled in a period of time. That's got two things in it. It's got distance and time. These are the fundamental properties. And anything that contains multiples of these gets to be in this column. So you can make this column like infinitely large by mixing and matching these things right here. What's here, there's a very, very small amount of things that are fundamental to the universe. And then this could be an enormous list. Oh, we're going to talk about mass. Okay. It's impertinent to ask how much somebody weighs. How do we measure weight?
Here we measure it in pounds and
In pounds.
stone.
Yeah, then the UK, they have a thing called stone. So here's where it all has to go away. There's an ounce, there's a pound.
Gram?
Gram's metric, so we're going to go to that. How many ounces are in a pound? Do we even know? Okay, so we don't even know what the conversion factor is. So that means, listen, we can't do the math. That answers 16, right? There's 16 ounces in a pound. And then pound gets turned into a stone. How many pounds are in a stone? 14. Who knows the 16 times table? So if I asked you what are 7 16s? What if I asked you what are 43 16s? Okay, so we need a 16 times table to convert between these two, and we need a 14 times table to convert between these two. Do you know your 14 times table? What's 49 times 14? We don't know it. Okay, and then how many stone in a hundredweight? We don't know. And then how many hundredweight in a ton? I don't know. Okay, so let's just agree that that is a really lousy system of measurement and not use it anymore. Let me ask you a question. How many milligrams do you think are in a gram? 1,000. How many grams do you think are in a kilogram? 1,000. Guess which times table the thousands are in? It's on the 10 times table. So if I give you any number and say, can you multiply that number by 1,000? You know the answer. What's 49 times 1,000? 49,000. Yeah. We can do grams and milligrams and kilograms because the math is shockingly obvious. Obvious. It's in intervals of 1,000. Can't do it. Cannot do it with ounces and pounds and stone and hundredweight and tons. Cannot do it. Okay. Mass, not weight. Let's pretend that marker right there has a mass of 1 gram. It weighs 1 gram. We take that pen over to the next building and we measure its mass over there. It's still 1 gram. And then we take it into space and we measure its mass in space. And it's still 1 gram. But how much does it weigh in space?
Less because of the gravitational difference.
It's weightless in space. It's weightless because it's floating. Weight is how mass expresses itself to us on this planet by being pulled down to the planet's surface. So for all of us, weight and mass are interchangeable. You can go throwing those, if that has a weight of a mass of 1 gram, it has a weight of 1 gram. Those numbers are interchangeable until you leave the planet. And because scientists and engineers devise objects that leave the planet now, we don't talk about weight anymore. We talk about mass, because mass is mass is mass. That the space shuttle, well, that's not a thing anymore. It can go up and come down. And when they build another one, it will. Space shuttle on the ground might weigh 10,000 tons. In space, it weighs nothing. On the ground, it has a mass of 10,000 tons. In space, it has a mass of 10,000 tons, because the mass tells you this is just a counting up of all of the atoms that made up the matter that got put into that object. Okay, so mass is just a reckoning, it's just counting up of all the matter that's in the object, but weight is what its effect on gravity is. Two things I want to put on this table. There's one fundamental one left, and it's not obvious. It's always the last one to be picked out. Oh, that was very, very quiet, but it sounded like it was right. Sorry, he's through the, yeah. Energy. Energy is a fundamental amount. And then I've got a derived one. And the derived one is what we're going to spend the first 2 lab periods doing. Has anybody read ahead to see what the labs are? We're going to do an online exercise on this quantity next week, and then we're going to do a physical in-person exercise on this quantity in week 3. Has anybody read ahead to see what that is? It's called density. And density is something really important to chemistry and physics, because it tells us intuitively as humans, because we've grown up with tactile animals. We touch a lot of things and we pick things up and we move them from place to place. And we know that if I'm going to pick an object this big up, and my brain tells me that this is paper, so I'm already prejudiced before I pick it up, then I'm going to expend this much energy, right? And if this were a fake book and it was made out of polystyrene, but it was the same size, same physical size, but it had less mass, then I would be surprised at how easily I could pick it up. That's an expression of density. It's how heavy is this divided by how big is it? What's its volume? And we had teased what volume was and said, wait a minute, why does it belong in this column? What is volume? Okay. There's an object. It's a geometric shape, right? That's a rectangle. That's a rectangle. That's a rectangle. This is a geometric shape. How would we express its volume? Yeah, but what dimensions go into? It's a 3-dimensional shape, right? It has a height and a width and a depth. And if I multiply the height by the width, I find the value of the area of the front cover. And if I multiply by the depth, then I get the volume of the whole thing. So volume feels like it might be a fundamental unit, but no, it's not, because volume is a distance times a distance times a distance. It's a length times a depth times a width. Let's see if we can put some units to these things. The units that we use are called SI units, Standard Institute. The Standards Institute are a bunch of very, very clever people who get together every now and then and decide it is in society's best interest that we don't use ounces that the gram is a better measure of mass than an ounce is. And then they collectively agree that everyone in the world will use this quantity. And then the Americans ignore it. We've tried. We've tried. It's implausible that it doesn't succeed because it's just too much work. It's so much more work not to be metric. It's part of the, well, I don't know what's going on because I'm not metric. I just don't get it. And at some point, you know that part of your brain that says, this sounds like math, I'm not going to listen. I'm just going to sit still, and if I sit still for the next couple of minutes, maybe the math will go away. That's using the old system. The metric system is just, can I divide this number by 1,000 or multiply this number by 1,000? That's my answer. Numbers are just numbers. Temperature, temperature is something that we should probably do last. Distance is in meters. Meters is a lowercase m, meters. And here's another, it never ends. Yeah, I live here on purpose. So from time to time, I will say things that sound like I'm critical of the United States, but I live here on purpose. I came for a reason because I like it here, especially in Texas. But you do a few things that are kind of odd and confounding. And here's one. Do you know how you spell meter? Spell it out for me. It's not how you spell meter, but that's how we've decided that we're going to spell meter.
R-E.
Yeah, it's the same way as, how do you spell theater? T-H-E-A-T-R-E. Because it's a French word. And as much as it pains me to admit this, because I was raised British, the meter is French. British hate French. We have a long-standing, friendly rivalry. I was going to say, now that we're in the European Union, we're no longer in the European Union, so they can go back to what they were before. Yeah, the British and the French just don't get along. So it kind of pains me that this is a French word. Everywhere else in the world, that is spelled R-E. X asterisk, except the USA, where we spell it E-R. No biggie, no matter. It's just like you've misspelled theater, T-H-E-A-T-E-R.
Or like color has U.
Yeah.
U-L-O-U-R-E.
You just took. Okay, meters. We've already discovered that there are 1,000 millimeters in a meter and there are 1,000 meters in a kilometer. I think we're off to a good start. What about time? What do we measure time in? Here's something, and I was reminded of this yesterday. I knew it, but I had forgotten it. I was reading Reddit yesterday. I'm reading in chapel on Friday, and the original text of the passage I'm reading said that Jesus shows up at the well in the 6th hour. What does that mean? If I told you, yeah, I'll meet you at the well at the 6th hour, what do you think that means? It could mean 6 a.m., but it also could mean 6 p.m., right? And it doesn't mean that. It means noon. The Roman system of time was not a uniform measurement of time. How many hours were in a Roman day? Anybody know? There were 12. There were 12 hours in a day. And what constituted a day? When the sun was up. So nighttime was not measured. Only daytime was measured. And every day was 12 hours long. And you know how in the summer, days are longer than they are in the winter? Still 12 hours. So an hour compresses and expands to meet the amount of daylight available. And you would say, you know, I'm just going to split the day in half. 6th hour means in the middle of the day. Yeah. So you think time is so fundamental. Our concept of time is so fundamental that time is constant. Well, not to the Romans, it wasn't. Not to the Romans. Time was a movable, measurable thing. Okay. We measure time in seconds because seconds are decimal. Minutes are not decimal. There are 60 seconds in a minute, and there are 60 minutes in an hour, and there are 24 hours in a day, and there are an indeterminate number of days in a month. And there's 365.25-ish days in a year to allow for the leap year. So the only thing that is decimal about time is the second. I'm going to ask you a question to see if you can figure it out. How many milliseconds are in a second? 1,000. It's not going to be a trick question. There are 1,000 milligrams in a gram. There are 1,000 milliliters in a liter. There are 1,000 milliseconds in a second. This is the beauty of the metric system. Mass, not ounces, not pounds, not stone, not tons. Grams, lowercase. And there are 1,000 milligrams in a gram, and there are 1,000 grams in a kilogram. Temperature.
Kelvin.
There are 2 temperature scales. 2. One is called Kelvin. It's a capital K. It's named after Lord Kelvin. Grams and seconds and meters are lowercase letters, but Kelvin is an uppercase. Okay. And it's a temperature scale that we need because it never goes negative. There are no negative numbers on the Kelvin scale. Temperature is always a positive number on the Kelvin scale. And when we do math, when we look at gas behavior later on, and we say that volume and temperature, if I've got a gas, and you know this already, you just might not know that you know it. If I have a balloon of gas, and I stick that balloon in the freezer, what happens to the size of the balloon? It shrinks. And when I take it out and put it in a hot car, it expands. So volume and temperature have a direct relationship. When temperature goes up, volume goes up. Now, if I'm using a temperature scale that has a negative number on it, the math implies that my volume goes negative. But if volume is a number times a number times a number, it can never be negative. Can't have a negative number. So volume can't be negative. Therefore, we need a temperature scale that never goes negative. So there are 2 temperature scales. One's really easy to use, and one's the right one for the math. This is the right one for the math, and the other temperature scale is
Celsius.
Degrees Celsius. This is not degrees Kelvin, just Kelvin. The other one is degrees Celsius. And the Celsius scale is really cool because it runs from 0 at ice temperature to 100 at steam temperature, and it expresses just about everything that we're ever going to experience. Cold as ice, hot as steam. Water freezes at 0, water boils at 100. A nice hot day in the upper 20s. Room temperature, 25. So hot that I can't touch it anymore, 70 degrees Celsius. Human pain threshold, 70 degrees Celsius. You may have heard that there is another temperature scale. You might have heard rumor that there's another temperature scale. There isn't. There isn't. Don't be fooled into thinking that there is any other way of measuring temperature other than Kelvin and Celsius. No country in the world, asterisk, except the USA, uses anything other than that as its day-to-day measurement of what temperature is. And they all use this as the scientific. That other one that you might have heard of, the F word, we don't use that. We just don't. And you can start today. You can go, when you get into your car, you can change the settings in your car to stop it reading from that scale into Celsius. So you can just start adjusting your mind to it. You can set your phone to read in Celsius instead of reading in that other scale. I'm not even going to say its name. It's that ridiculous. I'm not even going to say its name. And you learn, oh, good grief, today's going to be in the 30s. Again. How cool. I like it. All right. Everything in this column is derived from what was in that column. What do you think speed is measured in? Meters per second. Meters per second. Now, we have this little formatting thing that we do, that instead of saying meters over seconds, because that takes up too much space on the page, sometimes, not all the time, we do this. We multiply the two numbers together, but we've turned one of them into their reciprocal. So we're going to take the second, and we're going to raise it to the power of -1. And when you take a number and you raise it to the power of -1, that's the same as saying 1 over that number. Okay? So meters per second, or meters per second, is the same as meters times reciprocal seconds, which is meters per second. Okay? That might be the first time you've seen that. We'll see it again. Pressure. Now, pressure really is about newtons and meters and surface area, but we have a number that all funnels down to, and it's in atmospheres, ATM, atmospheres, and we use that number because it's simple. Guess what the gas pressure is inside this room? Yeah, like somebody at the front raised a single figure, just one. The atmospheric pressure of all the gas inside this room is 1 atmosphere, because that's what we've set it to. That's a really good definition. We're going to keep it. The actual definition, so this is atmospheres. The actual unit that we're supposed to use for pressure is called the Pascal. So uppercase P, lowercase a. And there are 101,300 and change pascals in an atmosphere. So it's much more precise than an atmosphere. And we have math that works for both occasions. Okay.
Do we need to know that conversion?
No. No. When you come back and you take physical chemistry 4300, we'll be using pascals. Everything through general chemistry uses atmospheres.
Does that include organic?
Volume. What was our unit of volume? Guess how you spell liters? L-I-T. Oh, you spelled it wrong again. Yeah, these words that end in er, the original French has them R-E. Takes a little bit of deciphering to read it sometimes. I'm going to skip over force because we're not going to use any force in chemistry. The only force that we use in chemistry is associated, it's built in to pressure. But I am going to talk about density, and you're going to do a couple of exercises on density. Density is mass per volume. So what would its units be? Oh. Thank you for reminding me of something. We've got to come back and just tweak that value of volume for just a second. If we find mass, oh, I didn't do the energy. Oh, good grief, look.
Right?
Yeah, so energy, look, I've missed something. Energy is measured in joules. I just completely blanked and missed that one. But our unit of mass is grams, and our unit of volume is the liter. But it turns out those two are mismatched. That a gram of substance usually is a small amount. You can hold, it depends what it is. That's what density is all about. But it's going to be a small quantity. And then a liter's kind of a big chunk of volume. So mostly we're going to use grams per milliliter. Okay. The milli in front is a lowercase m. The liter is an uppercase L. So that is grams per milliliter. Okay, so we're going to talk about volume for just a second, because we had a really good guess at the front of what might be here in volumes. Someone said cubic meters, which is a measure of volume, because any distance cubed is a volume. Well, it turns out that if you take a centimeter and then you make a square out of that centimeter, I have a 1 centimeter squared area. And then if I make that into a cube by making this distance 1 centimeter, then I have 1 centimeter times 1 centimeter times 1 centimeter is 1 cubic centimeter. Cubic centimeter. Cubic centimeter. Cubic centimeter. Have you heard of cc's? Who owns a motorcycle? Who aspires to own a motorcycle? What type of motorcycle do you want? 1,500, what? It's enormous. 1,500 cc. So when people talk to you about motorcycles, they talk about the displacement of the engine. How big of a volume is inside the piston of the engine? And that's measured in cubic centimeters, which is also a milliliter, which is fantastic news because we can now just turn meters directly into liters because of this link that a cubic centimeter is a milliliter and there are 1,000 milliliters in a liter. Okay? Questions? Because we'll leave it at that. I was going to show you a couple of other things, but we'll throw those in on Friday about, now that we know what to measure, here's what we'll do Friday. Let's start measuring things and do it wrong and then have to go measure it again. Okay?
What about CCs and like someone is going to receive this number of CCs of like,
Yeah.
like
Yeah, so if you went to the,
saline.
yeah, you went to the doctor or the nurse or the emergency care, they would administer a drug or, you know, saline to you in cc's, milliliters. Milliliters. It's cubic centimeters. Okay, see you all Friday. Don't forget, if you have lab tomorrow, use that time productively. We're not going to be meeting in person. Again? Friday, we'll go through some measurements. We'll look at error, two different types of error. And, I'm going to talk about, and then I'm going to talk about density.
Okay.
This is where the math finally kicks in, but the math is only take this number and divide it by that number.
Okay.
Okay?
Yeah.
It's not,
That's not hard.
yeah,
Okay.
it's not rocket
Totally.
science.
Awesome.
Okay.
Okay, thank you.
Is math difficult when we get into organic chem?
There is no math in organic chem.
Real?
Yep, none at all. That's why it's so fabulous.
Well, then,
It is all abstract. It is, can you look at this shape and can you make sense of the shape?
I was terrible.
It's logic. It's what you need for organic.